Okay, welcome back, and welcome to one more day this week in nonlinear differential equations. We're moving on to section 10.4, which just introduces the nonlinear differential equation, kind of in a slightly abstract setting. Similar with those Cauchy problems like we had for the linear differential equation. Unfortunately, we don't know how to solve these anywhere close to as well as we did with the linear cases. So I'm going to start out the same as before with the autonomous Cauchy problem. And it looks almost the same as before, except before we had something like Lx here, right? And in this case now we have n of x, some nonlinear operator of x. So the time derivative of x nonlinearly depends on itself. That's basically what's going on in the autonomous Cauchy problem. I want to make a quick mention, I know I have a remark on this later. This includes non-homogeneous with constant forcing. Okay, because a nonlinear operator on x could be some, maybe not use m, some other nonlinear operator, let's say capital F of x, so it's equal to a nonlinear operator plus a constant, you know, in the vector space. That's a perfectly valid nonlinear operator. So if I have a constant forcing in this problem, right, there could be a plus c constant forcing hiding inside of n, because we're allowed to do that now with nonlinear operators. So you know, this idea of homogeneous, non-homogeneous isn't as well defined for nonlinear cases as it was in the linear setting. So that's why I'm only focusing here on autonomous. We still have that n, capital N, does not depend on time. Okay, so autonomous systems, n will still not depend on time. It only depends on the place, the spatial coordinate, x. And I provide an example of this. This is a very classical nonlinear system. We're looking at the Lorentz system. This is the one that produces that really pretty butterfly, if you ever see its attractor. Something like that, really pretty butterfly attractor. It has nothing to do with butterflies, even though people will use it for the butterfly effect as well. The attractor is a result of, it's a system which models convection. So it doesn't actually have to do with butterflies, but it looks like a cute little butterfly, the attractor. Anyway, this system is a nonlinear autonomous Cauchy problem because here's the construction of the system. You can see it's a system of three differential equations which are coupled to one another. I have y in the first case, I have x and z in the second case, and I have an xy in the third case. So they definitely, each case depends on each other, right? As well as themselves. And so they're coupled, they're a system of ODEs, but they're nonlinear because there's a multiplication of two dependent variables, but unknowns, and then there's a multiplication of two unknowns. So we have two bilinear terms here, and the rest of the terms are linear. So maybe I'll circle those, and then we'll come in with blue and say these are linear terms. The ones in red are bilinear terms. Linear terms. Right, because a single multiplication is bilinearity, zero multiplications is linearity, and so we have basically a sum of some linear and bilinear terms here. So if you want to represent them explicitly, you can represent the bilinear terms as basically this is like a dot product with a specific matrix in each setting on the B, right? So if I go back to where my bilinear terms were, this is basically saying, okay, I have an interaction of x3, which is z, interaction of z with an interaction of x. There's a -1 times -1/2. I have an interaction of z with x times a -1/2. You add those together, you get negative zx in the middle coordinate. Look at that, there's my negative zx in the middle coordinate. So that's how this B gets represented. This is just one possible way of representing bilinear operators. There are all sorts of ways of representing them, but this is how I've chosen to do it here. And then L, my linear operator, thankfully can just be represented by a matrix. So that's those operators here. Another way of thinking about this would be like B of nm1 in my bilinear representation. This is B nm2. This is B nm3 in my bilinear representation way that I can do that from section 1 here. Okay. So there's the Lorentz system. This is just me being a little bit clearer about, hey, that's a nice example of a nonlinear Cauchy problem. This is why these are important. If I move onwards, we get to the nonlinear non-autonomous Cauchy problem. And this time we allow n to depend on time. Okay, so n can evolve in time now. And definitely this takes care of all the rest of the homogeneous cases, because I could just always add a forcing term that depends on time, and that's still just a member of a nonlinear operator. So we only have two styles of Cauchy problems in the nonlinear setting, the autonomous and the non-autonomous Cauchy problems. So if I grab my Lorentz system and all of a sudden I decide to force it with a function which does depend on time, right, now I have a forcing function here. You used to say that this, back in the linear section, you'd say, oh, this just makes it non-homogeneous, which is kind of true, right? It's definitely non-homogeneous, but it really is just non-linear, non-autonomous, because a constant function is a non-linear function. So there is a non-linear term here that depends on time that is in the system. So, but otherwise everything looks the same, and so you can technically, if you wanted to, represent the system as the following. And in this form, it takes it feels, I don't know if it's actually true, but this, looking at a function like this or a differential equation like this, almost looks like it should be easier to solve than looking at a differential equation like any of these above. Like this system looks really tricky to solve, and for some strange reason, this just feels like it should have an easier solution, which is kind of true, but it's like only a little bit true, right? Because if we want to apply theorems, we would maybe apply theorems to something like this. Okay, and primarily we're not going to be able to get the beautiful matrix exponential solutions that we had before when it came to linear Cauchy problems. There are two solution methods, which I'll provide, one today and one in the next lecture. And the one today relies on the following definition. So this definition is called dissipativity, or a dissipative operator. So if I have a nonlinear operator, it can be linear as well. So if I just have any operator on a normed vector space, so just think of like R3 with your classic Euclidean norm in R3, we call n dissipative if the norm, so this is like the Euclidean norm in R3, the norm of 1 minus lambda n on V. Okay, how should I interpret that? Let's make sure we know how to interpret this correctly. This is the vector V minus lambda times n intaking V. Okay, because it's not linear, so it doesn't really look like that, like n acting on V, but it's n intaking V. The norm of that, if that's always bigger than or equal to wherever V started, that's called dissipative. It's just a definition for now, but then I'll explain the intuition around it in a little bit. We also call it maximally dissipative, sometimes M dissipative, if the range of that operator on the left is the entire space. Okay, so this is basically saying that it doesn't, this specific operator here doesn't make anything smaller. And then this is lambda, this is only positive lambdas, by the way. This doesn't make anything smaller for positive lambdas. And even more so if the range of that operator is the whole space. Then we call it maximally dissipative. The intuition here, now we'll get to the intuition. In some sense, the dissipative operators are those which approximately reflect through the origin. That's what I want to think. Dissipative operators are taking some vector in a vector space and they're punching it through the origin. They're flipping its direction somehow. And now it's facing in the other direction from the origin. But it can do that non-linearly. That's kind of the important thing, is that it's allowed to do that non-linearly. So some weird things can happen to the vector, but wherever it happens to end up is like on the backside of the origin from where it started. Okay, so if we look at an example of that, the negative cubic monomial would be an example of that, right? So x cubed is definitely non-linear. It would need to be to the first power to be linear. And if I make it negative, then it becomes dissipative, because it's, in some sense, what does x cubed do? Well, it cubes something, but then the negative pushes me across the origin, right? So approximately reflected through the origin, the negative x cubed is going to do that for me. And I can prove that directly just by computing the norm of 1 minus n on x, which would be the 1 on the x gives me an x, the n on the x gives me negative x cubed. And so I get x cubed plus x, which is the same as x times x squared plus 1. And if I compute the norm just in R of this, I get the norm of x times x squared plus 1. And since x squared plus 1 is always greater than or equal to 1, right? This is always going to be greater than or equal to x in magnitude. So that makes it dissipative, and actually I can compute the range of n as the entire space, because actually, this is just by the intermediate value property, because 1 minus n at 0 is 0, and it also reaches plus or minus infinity, and it's also continuous. So any function that reaches 0 and plus or minus infinity, actually I didn't even need 0 there, I guess. Any function which reaches both plus or minus infinity and is continuous by the intermediate value theorem reaches every number. So yes, the range is everywhere, and so it's maximally dissipative. And so that's really nice. And then here's my main theorem, okay? This is the best we have for, I'll write this down right now. One of the best we have. The best theorems we have, maybe I should say that I've actually found, because this sort of thing is not covered in a traditional ODEs course, and actually even my graduate ODEs course, we didn't cover a theorem like this. So to the best of my knowledge, this is one of the best theorems we have for nonlinear Cauchy problems. And it says if n is maximally dissipative, actually I guess it just says dissipative. If n is dissipative, then the solution to the Cauchy problem is given by the following limiting procedure. And a lot of you might be looking at this and seeing that this almost looks like e to the nt, right? The limit in some sense there looks like my limit for the exponential in the limiting procedure, not necessarily the limit for the exponential in given as a Taylor series, but like the one that we started with when we were maybe in 11th grade or something, talking about continuously compounded interest. It looks like that limit, which I think is fascinating, that it actually does produce something that behaves kind of like this. But don't think about it like that, because we were already rocking the boat defining it as the matrix exponential. There's really should not be a good interpretation of this as a nonlinear exponential. So I don't want to think about it like that. But yes, it does look very similar. I agree with you. So actually the solution can be given by this limiting procedure. And moreover, we have a nice property where the solution can at most grow, like the difference between the solution at 2 points in time can be at most the norm of the operator at the initial condition. So that's really nice as well. You get some sort of growth properties. And actually you get decay properties here. So finally, the limit actually decays to 0. So that's a dissipative operator property for Cauchy problems. And I have a remark talking about it like exponentials, even though you shouldn't think about it like exponentials. But the next example is pretty cool, because it says, hey, let's see this in practice. Let's solve this Cauchy problem. So we've got our Cauchy problem here, and let's solve it. And we can solve it because we already know from the previous example that this is a maximally dissipative operator. So I'm totally okay solving this Cauchy problem using this technique, but what would it mean to calculate this as an operator? It's like the identity minus t over n, and then I'm cubing something, and then I actually have an inverse, right? The negative n power is an inverse operator. So I'm going to take an aside to calculate this operator. Something I can start with is the inside. So the inside is an operator, 1 minus t over n, my nonlinear operator there. Looks like x plus t over n, x cubed, which I can rewrite as the following if I want to. And if I invert that function, this is maybe why the cubic formula is useful. So, we had that cubic formula above. You can invert this function with the cubic formula, you get the following. It looks really terrible. Nobody would want to actually use this, but hey, we've computed it, and let's take it to a few powers. If I took it to infinitely many powers, this inverse, and this is function composition, by the way, in the x variable. I want to maybe make that clear. So the n there is function composition in the n x variable. So every x there, all of those x's, I'm doing function composition in the x variable when I compute n of those. If I plot the 10th iterate or approximation against the true solution, let's see what it looks like. So the true solution, by the way, is 1 over root 1 plus 2t. So I compute the 10th iteration, there is my approximation, and I'd say that's pretty darn good, right? That's the one in red. So you can see that they get really, really close to each other. It's a little bit fascinating that you can compute iterates of this just really ugly function, and I compute 10 iterates of that, and we get something that's going to converge to my actual solution. So this section, I don't even think I have any exercises on using this theorem itself. I do have a brief exercise on you proving something about dissipativity, just because this stuff is so abstract and out there that we don't hardly use it very often. The next section, this existence and uniqueness of nonlinear solutions, is going to be much more useful for us. So we'll move on to the next section soon. I'll see you then. Bye.